Hello and welcome to this week's episode of the Metabolic Classroom. I am Professor Ben Bikman, biomedical scientist and professor of cell biology. Today, the classroom is going to be focused on one of the more common metabolic problems, and in particular, a metabolic problem of the liver. The liver is, I like to joke, it's the soccer mom of metabolism, which is like a busy mom within a family at the heart of everything. Nothing happens without the liver being involved with the process if it has to do with nutrient metabolism. The liver is unique because it can handle every nutrient, whether it's making the nutrients or storing the nutrients or burning the nutrients. It is unique in that it has its hand in all of them, even the random rare ones like lactate, or a little less rare like ketones, and then of course the big ones like glucose and fat. And it's the fat in particular that we want to talk about today. Fatty liver disease is the most common liver disorder worldwide, and at its core nowadays is a metabolic problem. Indeed, there is a new name that has been suggested. Rather than calling fatty liver disease non-alcoholic fatty liver disease, it's something a little more complicated, unfortunately, like metabolic associated disorder of the liver or something like that. But suffice it to say, call it whatever you will, it is a metabolic problem that results in the accumulation of fat within the liver. There are implications that go beyond just having fat in the liver. And that is what the fatty liver can turn into. So this is an idea or a problem that is a gateway problem, where once the liver starts to accumulate fat, it has opened the door for more serious liver problems to begin. For example, non-alcoholic fatty liver disease can then progress into non-alcoholic steatohepatitis, or NASH. And what was once just a fatty liver is now become a fatty and inflamed liver. That's the hepatitis. Anytime you hear that suffix itis, think that whatever the previous part of the word is referring to, it's inflamed. And then once the liver is fatty and inflamed, then it can become scarred, which is fibrotic or liver fibrosis. And then you get to cirrhosis, which is much more serious. So again, one of the reasons it is valuable and worth our time to talk about fatty liver disease is just because of what it can turn into. As I already mentioned, it is the most common liver problem worldwide, and it actually affects about 1 in 4 people. So 25% of all people have fatty liver disease. So this is a shockingly common problem. And of course, it is closely mirroring other metabolic complications like obesity and diabetes. And of course, underlying all of this is insulin resistance, which brings us to the first of the meaty topics within this broader topic. Now, let's take a moment and discuss what insulin resistance is. Let's define it again, because we need to appreciate the two components of insulin resistance to appreciate the metabolic milieu in which fatty liver disease is happening. So insulin resistance is a problem with 2 parts. It is a 2-part pathology or disorder. On one hand, we have the fact that insulin isn't working particularly well. That is the insulin resistance part of this 2-part problem. And remember, that's not a universal phenomenon. That is not a global phenomenon happening within the body. In other words, some of the body's cells are responding to insulin as well as they ever were, but some aren't. And thus we have the insulin resistance part of this definition. But at the same time, and indeed in the context of fatty liver disease, this part of insulin resistance is more important. We have chronically elevated insulin levels, a condition technically known as hyperinsulinemia. Anytime you hear that end of the word emia, that means in the blood. Hyper, of course, means high. So high insulin in the blood. That is the second part of insulin resistance. or the first part, depending on how you want to define it. But regardless of where you put it, it is an essential part of what we call insulin resistance. There is no insulin resistance without hyperinsulinemia. The two are inseparably connected. And again, in the context of fatty liver disease, it is an essential component to understand why the liver is getting fat. So let's move into then the actual fattening of the liver. Let me just make a declarative statement, and one that is intended to be very bold, which is that the body and the liver cannot store fat unless insulin is elevated. Ultimately, while there may be an acute accumulation, depending on other stimuli that we'll talk about later, specifically fructose and alcohol, that fat won't linger unless insulin is elevated. So it becomes increasingly impossible for the liver to be fat in the absence of elevated insulin. So to say that another way, it becomes ever more difficult for the liver to keep fat in itself as insulin is coming down. Insulin is a necessary either stimulus to put it there in the first place, and we'll discuss that, or to keep it there to prevent it from breaking down. Now, again, I mentioned two key inputs here, fructose and alcohol, and we are going to spend time talking about those because they are worthwhile. Alcohol does matter, and as much as we've been framing this from the non-alcoholic side, we're just going to generally discuss fatty liver disease, because even the alcohol component is a component of nutrient metabolism. So that would still technically fit within this new definition of metabolic dysfunction associated fatty liver disease, or whatever it's technically being called now. So again, the key opening statement here is that the liver cannot hold on to this fat unless insulin is elevated, because insulin just has this authoritative power over what cells of the body do with insulin, what the cells of the body do with energy, fat included. Now, there are two pathways that predominate with regards to the liver becoming ever fatter. One pathway is fat that is being leaked from adipose tissue in the form of free fatty acids. So that's one key input into, in this case, directly pulling in fat from the form of, from free fatty acids, and then storing those fats within the liver. And as I alluded to already, and indeed in previous episodes, anytime you are talking about free fatty acids, you are talking about fat that is being broken down from fat tissue through the process called lipolysis. So lipolysis of fat tissue, of the fat within the fat tissue, to be a little more precise, will result in the release of free fatty acids. And then those free fatty acids are going to flow to the liver, and then the liver can readily pull them in and store them. Now, there's a little more nuance there, and it once again will be incumbent on us to discuss the role of insulin. But before I get into that, I wanted to mention the other one, with the other source of fat, which is the liver making its own fat. That is a process called, within the realm of nutrient biochemistry, de novo lipogenesis. So basically making fat from scratch within the liver. And this happens from excess carbohydrates. Essentially, if the liver has filled its glycogen reserves, then so its stored form of glucose, then the liver, and that's a about 100 grams or so, depending on the size of the liver and the individual. So once the liver has filled up its glycogen, so the stored form of glucose, then it will readily start converting that to fat. Now, there's another carbohydrate, namely fructose, which doesn't need to wait until the glycogen is filled and can simply directly contribute to fat storage. And we'll revisit fructose more in just a bit. Of course, insulin is, once again, totally essential, that you aren't going to be even activating the pathway, the series of steps that promotes the growth and the development of fat within the liver unless insulin is elevated. So elevated insulin is an essential signal to turn on that process. So both of those are contributing. Now, I want to highlight two studies that actually looks at the influence of each of these signals. Again, the uptake of free fatty acids and the de novo lipogenesis. So the liver pulling in fat to store, and then compare that with the liver making its own fat to store. So one study, and this is Lambert et al. Lambert is the name of the first author, last name of the first author, 2014. And this study highlighted that subjects with fatty liver disease had more than a 3-fold higher rate of de novo lipogenesis, so synthesizing new fats, than subjects with without high levels of liver fat. So people that had higher liver fat had a 3 times higher rate of making fat within the liver compared to those who did not have fatty liver disease. And what's interesting, and something that we're going to talk more about in a future episode when we talk about saturated fats, is that when the liver has been told to make fat, it always makes one type of fat, and that is palmitic acid or palmitate, which is the majority of the saturated fats we have in our body, including the fats that are circulating in our blood within triglyceride-rich molecules like in LDL. So anytime people are talking about the problems of saturated fats in the blood, the inconvenient truth for those individuals is that most of that saturated fat is coming from what the liver is making. So again, we see that in people with fatty liver disease, they are making a lot more fat within their liver, 3 times more than people without fatty liver disease. So strong indication, strong evidence that de novo lipogenesis, or the synthesis of new fat, is a clear and relevant variable in people with fatty liver disease. Now, to directly compare de novo lipogenesis with free fatty acid uptake, another study, and this is Donnelly et al. In 2005, they documented that in fatty liver disease, approximately roughly 60% of all of the fat in the liver came from free fatty acids, as opposed to almost 30% from de novo lipogenesis. And then that smaller portion, whatever left, coming from what was circulating from the diet in the chylomicron. So well over half of all of the fat going into the fatty liver is coming from the free fatty acids from the fat tissue breaking down. And then about half of that amount is coming, when comparing them, is coming from de novo lipogenesis. And then don't forget the study I just mentioned previously, indicating that if someone has fatty liver disease, they're making 3 times more fat than the person who doesn't have it. And of course, there are a variety of factors that play into this. Now, let's really revisit insulin. Insulin, let's start at the fat cell. And we've talked about this previously, but why is the fat cell undergoing lipolysis in the first place? Normally, in an insulin-sensitive individual, so a healthy, metabolically flexible person, free fatty acids are always going to be the inverse of whatever insulin is because of what insulin does to lipolysis. Specifically, insulin inhibits lipolysis. Insulin inhibits the breakdown of fat, and it does so exceptionally well. Even a modest increase in insulin is sufficient to slow down lipolysis and inhibit it. Thus, in a state where insulin is elevated, free fatty acids will be very, very low. In a state where insulin is low, now there is no longer an inhibition of lipolysis, thus free fatty acids will be elevated. So in a healthy, insulin-sensitive, metabolically flexible state, again, insulin and free fatty acids will always be in the opposite directions. Now let's just continue with that thought for another moment, because now, if insulin is low and the free fatty acids are elevated, why are those free fatty acids not contributing to fatty liver disease? In other words, if someone is fasting, why at the end of their fast is their liver actually leaner if they fast for 24 hours? There's less fat in their liver than there was before the fast started. Because now, can you see the problem? If it's just all about what's the availability of the free fatty acids, then it should be fatter. So you fast, your insulin comes down very quickly, minute for minute. Fasting is the fastest way to lower insulin. There's no debating that. And during the fast, as insulin's coming down, no surprise, free fatty acids are coming up. That, based on how I've in this very simplified manner described it, that should be contributing to fatty liver disease, right? But again, at the end of, say, a 24-hour fast, the liver is not fatter, even though free fatty acids are very high. Remember what I said very early on, even in this discussion, let alone many, many previous, that insulin tells cells what to do with energy. And if insulin is low, even though the liver can still pull in those fatty acids, it will not store them. It will not push them into this pathway of turning them into stored triglycerides, the storage form of fat. No. So if you can't store the fat, what do you think the liver will do with it? It will burn it. It will burn the fat, because if insulin is low, it has no other option. And this is when we get into the realm of ketogenesis. So I hate to bring in a new process here, but this is when ketogenesis begins to occur, where the liver has all of this fat coming to it. And because insulin is low, it cannot store it. And it continues to burn fat, continues to burn fat. In fact, it burns so much fat constantly that the entrance of the fat to continue to be burned starts to kind of close up. It gets too full. This process of the citrate cycle, this biochemical process of ultimately kind of the end product of burning fat through the citrate cycle. The citrate cycle gets so full of fat burning that it starts to tell the rest of the liver cell, hey, I can't handle anymore. And thus the only other option opens up, which is ketogenesis. So ketogenesis is the end result then of the liver seeing a lot of free fatty acids, but not having, but having low insulin, and thus not being able to stop burning fat. Now, that's the fasted state or the low insulin state, higher free fatty acids coming from the fat cell, and the liver is just burning it. Now, when might there be a state? Based on what I described earlier, anytime insulin will be elevated, which is a necessary signal telling the liver to hold on to that fat and indeed to store it, to convert it into triglycerides to hold on to, that can only happen if insulin is elevated. But if insulin and free fatty acids are always only in the inverse, well, then you'd never have all of that availability of the free fatty acids unless the fat cells have become insulin resistant. Now, you'll recall from earlier discussions, when the fat cell has reached a point of hypertrophy that it can't really grow any further, it will start to become insulin resistant. And remember, insulin's main signal at fat cells is to inhibit lipolysis, to prevent the breakdown of the fat. But that's the very signal that gets broken as the fat cell becomes very insulin resistant. So now you have this uniquely harmful state where insulin is elevated, which would normally be inhibiting lipolysis, resulting in lower free fatty acids, but the fat cell isn't listening anymore. Now it's breaking down fat, even though insulin's trying to tell it to not break down fat. Thus, we have high insulin and elevated free fatty acids, and now it's the perfect metabolic storm. So now the liver is seeing all of these free fatty acids leaking from the very insulin-resistant fat cells, and the high insulin is now signaling to the liver, hey, you're getting all that fat. Maybe you wanted to burn it, but I'm making you store it, because insulin dictates fuel use within cells, every cell of the body, most especially the liver. Even though insulin has a modest impact on the liver of pulling in nutrients, it has a very strong impact on the liver's ability to release those nutrients. And in this case, it is a wicked combination. So the elevated insulin, reflective of an insulin-resistant state within the body, and the elevated free fatty acids, reflective of an insulin-resistant state of the fat cells themselves, together combine to tell the liver to basically overfeed the liver and not allow the liver to break down any of that fat, forcing it to convert it into the storage form of triglycerides. Now, so that's a lot of nuance there, a lot of complexity, and hopefully it makes sense. But remember, at the same time that insulin is elevated, why would the insulin be elevated? A key part of this is going to be the chronic and frequent spikes of glucose. And so then even still, in a case of elevated insulin with insulin resistance, very likely there's an abundance of glucose in this body. Otherwise, the insulin can't be elevated for very long. So we also still have the de novo lipogenesis being relevant here, because the chronically elevated insulin is going to be telling the liver, hey, you have a lot of glucose too. And so while I'm forcing you to store all of that fat coming from the insulin resistant fat cells, I also want you to continue to make fat. So de novo lipogenesis goes up a lot. And remember, in people with fatty liver disease, in the study I showed you earlier, it's at least 3 times higher than that happening in people without fatty liver disease. So free fatty acid intake forced into triglyceride synthesis to store the fat. That's happening as a result of elevated insulin. And just the pulling in of the glucose in the liver saying, hey, I already got a lot of glycogen on hand, so I'm just going to start converting this excess glucose into fat. And that's happening again roughly at half the rate or half the contribution that the free fatty acids are contributing. But even still, it all comes down to insulin resistance. Now, despite what I just said, let's talk about a couple signals that are a little independent of the insulin signal, even though insulin is still relevant. But these can operate somewhat independently. They have the ability to play by their own rules, and that is fructose and then alcohol. And again, alcohol does fit, as I said, within this metabolic definition because it is a function of metabolism that leads to the liver getting fatter. It's just a unique one. So just as another brief sort of history lesson that I perhaps could have started with, non-alcoholic fatty liver disease was a phenomenon generally of the mid-20th century, or maybe a little earlier, where we found that in the past, if someone had fatty liver disease, it was almost only because of their consumption of alcohol. And then there arose in the early-ish mid-1900s people manifesting with fatty liver disease and yet very little to no alcohol consumption. And that, of course, coincides very, very well with the consumption of fructose. So fructose is unique because unlike other sugars, specifically glucose, any cell can metabolize glucose. In fact, literally every cell of the body is capable of metabolizing glucose, but that is not the case with fructose. Fructose is almost entirely metabolized in the liver, thereby placing a unique metabolic burden on that organ. And the liver converts fructose directly into fat via de novo lipogenesis, leading to fat accumulation. And fructose metabolism in the liver generates metabolites that also, to even compound the problem, can trigger inflammation, and that's specifically uric acid. So one of the great tragedies of the modern view of gout, which is a problem of uric acid accumulation, is that we always focus on the meat. And while meat may contribute somewhat in some people, it is nothing compared to fructose. Every one molecule of fructose that a cell, the liver especially, metabolizes will give rise to a molecule of uric acid. So that's an enormous contributor. Now, some people want to argue that fructose is not a contributor to fatty liver disease in humans. While there is substantial evidence in rodents, some claim that humans don't metabolize fructose the same way. That's not wrong. We do. We do metabolize fructose somewhat differently than, say, mice and rats. But even still, to then take that claim one step further and say there's no human evidence is simply not true. And so just to directly address that, I wanted to highlight a few studies. So Lee et al. In 2009 published a report in the American Journal of Clinical Nutrition that looked at fructose overconsumption in people and then measured the degree to which the liver started making fat from it. And the study demonstrated that the high fructose diet, after just 1 week, just 7 days, led to significant elevations in the liver. So directly highlighting this direct effect. Another controlled feeding study by Schwartz et al. In 2015, it was published in the Journal of Clinical Investigation, which is a particularly high-profile journal. And the participants consumed beverages that were sweetened with glucose or fructose or high fructose corn syrup, which is almost, it's like 55% fructose, 45% glucose, although that can vary. There are different versions of high fructose corn syrup. And the study found that the beverages containing fructose led to increased liver fat and de novo lipogenesis compared to the glucose-sweetened beverages. And then a final study is Stanhope et al. In 2009. published in the Journal of Clinical Endocrinology and Metabolism, JCEM, another good journal within my field, and that investigated the results of consuming fructose-sweetened beverages for 10 weeks, once again, finding that it resulted in a significant increase in de novo lipogenesis, so within the liver. So another direct effect. So that's just a few of the several human studies that have looked at this. So once again, to just put a fine point on this part of the discussion, fructose is a contributor, and it doesn't have to rely on insulin's signal. Although, again, the elevated insulin would be necessary to tell the liver to hold on to that fat. Otherwise, the liver would simply begin breaking it down. All right, now let's move on. The final part of this discussion, let's move into, final part will be strategy. So the last part of the problem part of this discussion, let's talk about alcohol. Now, just as an opening part of this, it's important to remember that most alcohol that people are drinking has a lot of sugar or starch in it. There's a lot of carbohydrate coming with that. Now, alcohol is its own macronutrient. It is neither fat nor carbohydrate. It is its own thing. So when I'm talking about alcohol coming with a lot of carbohydrate, I don't mean that they're the same thing. I mean, it's pretty common to get sweetened alcohols. And the irony is I've never tasted a drop, so I don't really know. I just know from a purely academic perspective here. One of the things about ethanol, which is the alcohol part of this, is that when it begins to get metabolized through these what's called dehydrogenase enzymes, it will change. This is getting a little deeper into the biochemistry than I would like to, so I'll just be really brief and kind of superficial with it. But it changes what's called the redox state. So the balance of these equations, of these variables, these molecules that are oxidized or reduced, and it ultimately tips this in such a direction that it begins to inhibit the liver's ability to burn fat, to break down fat. So alcohol is mucking up the gears involved in fat burning. Also, ethanol at the same time is activating lipogenic enzymes, in particular one called fatty acid synthase. This is part of the de novo lipogenesis pathway. And then one final comment on alcohol is that it normally, the liver is capable of creating fat and then releasing it into the body on what is referred to as triglyceride-rich lipoproteins. And the most relevant of these being VLDL, which is then converted to LDL, which you've, of course, heard of. So that is one of the ways where the liver is moving fat out by sharing it with the rest of the body. And that is not a problematic process. It is a good and indeed necessary process. This is part of that soccer mom role of the liver, saying, hey, I've got some fat here. Let's start sharing it with the rest of the body, which is good. The body can burn that fat or use those lipids for any number of purposes. But ethanol blocks that effect. It inhibits the production of these triglyceride-rich lipoproteins, so blocking the assembly and the secretion of the VLDL, which ultimately forces the liver to hold on to more of its fat rather than packaging it and, again, releasing it. All right, so we have covered a lot here. And at the first part of it, when we were talking about free fatty acid uptake and de novo lipogenesis, I really hope my explanation of insulin and the dynamics of insulin feeding the fat and telling the liver what to do with the fat resonates and leaves an impression on you, because there's such a beautiful nuance there that as much as some people will say that the liver's getting fat just because the fat tissue is insulin resistant, well, that's just some part of the story, that you have to appreciate that within the insulin resistant body in a broader context, it's the elevated insulin then that is promoting or forcing the storage of that fat within the liver. And then, of course, we reviewed fructose and alcohol, both of which, of course, have very meaningful contributions. Now, what can be done? First of all, what can you even know? The best, most definitive way to confirm fatty liver disease is through some imaging, whether it is ultrasound or MRI. You can actually get a picture of the fat within the liver. That's not common. It's more invasive, more time-intensive and expensive. What is very, very common is measuring liver enzymes. Alanine aminotransferase and aspartate aminotransferase, often simply abbreviated in how you might know them simply as ALT and AST. ALT and AST are these enzymes that are heavily enriched within the liver. Now, just as a brief aside, they are also released from muscle tissue, which is one of the reasons why, if you're going to get a deep dive, thorough blood exam, do not work out really hard, at least within 24 hours and maybe even 48 hours, just to make sure you're not going to get a false positive. I speak on this topic with some passion because I once was told I had fatty liver disease, which was ironic, again, because I've never touched a drop of alcohol in my life, and I'm metabolically healthy. And I tried to convince the clinician at the time, this was many years ago, that it was simply because that it was a false positive, that it was actually just because I'd worked out too hard. And sure enough, a repeat blood test when I was a little milder with my workout showed perfectly normal levels. So just as a reminder, these enzymes are also expressed in muscle. So if you've done a lot of muscle work, you're going to be flagged as having fatty liver disease, even though your liver could be perfectly healthy. All right. Now, nevertheless, those levels do matter. And if the ALT to AST ratio, so take ALT and divide it by AST, if that's higher than 1, getting closer up to 2, that's generally viewed to be a sign of fatty liver disease. So take that for what it's worth. Now, what can you do? Of course, as usual, when it comes to metabolic problems, the standard of care is going to be drugs. So let me just talk about that very, very briefly. One of the most effective drugs for fatty liver disease is a class of drug called the PPAR gamma agonists. PPAR gamma agonists. You've heard me talk about these in a previous metabolic classroom. And it's interesting because these are a class of drugs that actually promote the synthesis of new fat cells. So it activates fat cell hyperplasia. Earlier, a moment ago, when I talked about the insulin-resistant fat cells, I used the word hypertrophy. When the fat cells undergo hypertrophy, they get really, really big. And when you take those really, really big insulin-resistant hypertrophic fat cells and then within the body inject or take in some PPAR gamma agonists, which is this class of drug I'm talking about, you now start reproducing fat cells. And so the fat cells can all get a little smaller, even though they are now more abundant. And remember, when it comes to insulin resistance, it is not the total amount of fat a person has, but the size of each fat cell that matters most. And so by taking a PPAR gamma agonist, the size of the fat cells are getting smaller on a person and they're becoming more insulin sensitive, which is then resulting in less free fatty acids coming from the fat cells, which is taking away the leading contributor to fatty liver disease. So it's no surprise, as you are helping the fat paradoxically store more fat, but also become more insulin sensitive, you are now sparing the liver. But again, it comes at quite a cost, where now the individual is getting substantially fatter. But again, that does spare the liver from having to store that fat. Now, that is the conventional intervention, which is going to be drug-based, but we are not conventional in our thinking here within the metabolic classroom. So at its simplest, the most effective strategy for reversing or preventing fatty liver disease is control carbs. By controlling carbohydrates, you are allowing insulin to come down. When it comes to eating, there's no better way to drop insulin. Now, of course, fasting matters enormously, but you can't fast forever. So when you do eat, control carbs. So try to focus on whole fruits and vegetables. Don't get your carbs from bags and boxes with barcodes whenever you can avoid it. So the lower insulin will help the body be more insulin sensitive, and it removes that signal to the liver to force the liver to store the fat, but also it will restrict fructose. Now, the fruit contains fructose, albeit relatively modest amounts. In some instances, incredibly modest amounts like berries, and in other instances like the tropical fruits, it'll have more. But just at its simplest level, you can think of controlling carbs as just eating whole fruits and vegetables. Eat them, don't drink them. So fruit juice is a highly concentrated source of fructose, which is not good for liver health for the reasons we've talked about, the contribution of fructose to liver fat. So control carbs. It'll help bring down the insulin, and it will naturally restrict fructose. And of course, control your alcohol consumption. That is the end. I hope that these ideas have been helpful, that you have a much, much better understanding of fatty liver disease. I am optimistic that we've covered the most relevant points, and you are now much more informed on the topic. And do your professor a favor. If I have effectively taught these principles, you should be able to teach them to someone else. So please do so. Share what you've learned with your friends and family any way you can. Talk with them about the metabolic origins of fatty liver disease. And as usual, thank you for the support. If you haven't, please be sure to join the community at insuliniq.com and go to the YouTube channel Insulin IQ and subscribe. Thanks again for tuning in. For those of you that have already joined as memberships, I will see you now on the live Q&A for everyone else. Thanks, and I'll see you next time.